Hello, ladies and gentlemen. We're going to do 7.1 today. We're going to be starting our chapter on revolved solids. So the first thing that we're going to talk about is the area between two curves. Our objectives are that we're going to find the area of a region between two curves using integration. Alrighty, so just to refresh our brains, I'm going to have two cute little curves. So I'm going to have a guy going this way, and we're going to call him f of x. And then I'm going to have a little guy going this way. We'll call this one g of x. And notice that their point of intersection is going to happen at A, and the other point of intersection is going to happen at B. So this is my area in between the two curves. Sorry. I'm going to draw my little rectangle, and this is going to be my delta x, and then the middle of the rectangle is going to be x sub I. So the height of the rectangle is going to be the difference in between the two curves. So it's going to be f of x sub I minus, because f of x sub I is the top curve. So I'm going to add a little top right there just so we see that, minus, the paper's weird, g of x sub I, which would be the bottom curve. Because if I subtract the top curve minus the bottom curve, I get the area in between. And then notice that, sorry, I'm still hoarse, the width of the rectangle is going to be delta x. All right, so then the area between the curves is going to equal f of, and I'm going to put it in parentheses, f of x sub I minus g of x sub I, because this is, oops, I need another parentheses, this is the height of the rectangle times delta x. So then if we talk about increasing the numbers of rectangles, then we talk about taking the limit as n approaches infinity, where n is the number of rectangles, for the sum from I equals 1 to n of f of x sub I, because we want to make it look a little bit more official, g of I, and then our delta x. And then, of course, I could do this using the limit process, and then you would have to remember your summation formulas for your i's. Or we write it as a handy-dandy little integral, a to b, and it is the integral of f of x minus g of x dx. Just a reminder about notation. Make sure that when you write your integrals that you always put everything that you are integrating with respect to dx inside of parentheses. Alrighty, so remember, if you will, in general, if I am going to use a delta x, like I have in this one, and have that be the width of my rectangle, then I'm going to do the top minus the bottom. Okay, so if I'm finding the area between curves, and I'm just going to draw a little rectangle, I have a vertical rectangle, which means I have a delta x as the width of the rectangle, then it's going to be the top minus the bottom, okay? And that would be this equation that we've already done. But on the other hand, if I have a sideways rectangle, so here's my sideways rectangle, and instead of having the width of the triangle be delta x, now it's going to be delta y, then this becomes typically the right curve minus the left curve. And so we would say that our area is equal to the integral from a to b. And remember, and actually I'm going to change that, and I'm going to call this c to d. And this would be my vertical points of intersection. And I would have f of y minus g of y. Oops, and there's my parentheses, dy. Alrighty, and so you have to pay attention to which way works the best. Do I do my delta x vertically, or do I do my delta x, I guess this would be a horizontal delta x, and this would be a vertical delta x. Alright, so let's start doing a couple of examples. So for our first example, it says find the area of the region, and it's going to be bounded by the graph of f of x is going to equal 2 minus x squared, and g of x is going to equal x. Sorry, you can't see that. So what we talked about in previous courses, it's really nice to look at this because it helps you to decide what you need to see. So we're going to draw a picture. Okay. So here's my handy dandy little graph. This is an upside down parabola with a y-intercept of 2. And so he looks like this. Ooh. Okay. There's that little parabola. And then if I have my line, y equals x, I think I'm going to need to make him a little bit longer. Then I have this guy doing something like that. So this is g of x, this is f of x, and I want to find the area of the region between the two curves. And so I'm going to integrate, this is a, that's that point of intersection, and then this is b, and I'm going to integrate from a to b. So I need to figure out where those two graphs run into each other, and that happens where f of x is equal to g of x. So in case you didn't have access to a grapher and you had to do this by hand, shocker, then you would set these two guys equal. I'd have my 2 minus x squared equals x. That's just a plain old little x. And then I would rearrange. A negative x squared minus x plus 2 is 0. Factor out the negative. X squared plus x minus 2 is 0. Factor x plus 2, and x minus 1 is 0. So x is going to equal 1 and a negative 2. So this point right here is 1. This little guy is my negative 2. So if I wanted to calculate the region between the two graphs, it's going to be my area is equal. I'm going to integrate from a negative 2 to 1, reading left to right because I'm integrating with respect to x. And then I'm going to do my top minus the bottom. So my top curve is f of x. And you can't assume that it's always going to be f of x. You actually need to look at your graph and decide which guy is on the top. And I'm going to do minus my bottom one, which is x, and then I'm going to have a dx. And then this is a very polite little integral to integrate and evaluate. So then I'll kind of come down here a little bit. This is 2x minus x cubed over 3 minus x squared over 2, evaluated from a negative 2 to 1. Miracles happen. I would be most unhappy with you if you did this on an exam, and you would get 9 halves. So the area would be equal to 9 halves. Since the problem didn't give us any units, we don't have to include any units, so that one's kind of done. That's nice. That was a nice short little problem. All right, for our next one, it says find the area of the region, gosh, I can't spell, between the graphs. And then the two equations are going to be f of x is equal to 3x cubed minus x squared minus 10x, and g of x, which is a negative x squared plus 2x. All right, so again, because you often have to do math without a calculator, let's graph these. And I actually cheated and used a calculator to find my graph. Okay, so my f of x is going to look something like this. There's f of x. And my g of x, which is just a little upside down parabola. Let's see if I can hit all the points that I need to. It's going to hit there. It's going to hit there. I'm going to do here. And there we go. That's a gross estimation of what it looks like. So then this guy is g of x. Alrighty. Then I have my area in between the curves. So I'm just going to color a little bit because we like to color. Okay. And then I want to talk about just looking at the graphs before we get started. So notice that my curve, so in this one, F is right here and G is here. So this is top minus the bottom. But when I cross this point right here, which happens to be 0, 0, we'll find that in a minute. But when I cross, now the top is G and the bottom is F. So since the curves switch places, which is often the case, it's really nice to split your integration up as you do the area between two curves. So what I need to do now is I'm going to find my point of intersection by hand, just because we can. Negative x squared plus 2x, which means those are the points where the functions are equal. So I get 3x cubed minus x squared minus 10x plus x squared. Well, that's a pisser. He goes away. Minus 2x equals 0. So I get 3x cubed minus 12x is 0. I'm going to factor out a 3x, and I get x squared minus 4. So I get x is equal to 0 and plus or minus 2, which those are the 3 points of intersection. So this little guy is going to happen at a negative 2. There's the 0. And then this guy is at the 2. Alrighty. So then if I do the math, and actually I'm not going to do the whole problem, but I am going to set up the integrals for you. I think you're brilliant, so at this point I'm assuming you can do that integration. But if I set up my area integrals, I would integrate from a negative 2 to 0, and I would do f of x minus g of x, and there's my dx. And then I'm going to add that 2, then I'm going to go from 0 to 2. But remember, the curve switched places, and I always think this is entertaining that I'm doing hand motions that you can't see. Sad day. So then I have g of x minus f of x. Again, it's the top minus the bottom, dx. And at this point, I'm assuming that you can substitute those cute little functions into your integrals and then integrate doing lovely math. Okay? When you're done, if you decide to do that so you can check your work, you get that the area is equal to 24, and that would be the area from a negative 2 to 2, in between the two curves. All right. So for our next example, and you lucky dogs, it happens to be your last example, okay, because this is the easy part of this chapter, we want to find the area of the region bounded by the graph and then we're going to have x is equal to 3 minus y squared and x is equal to y plus 1. So right off the bat, my video kind of turned blue. That's kind of trippy. Oh well. So I have a blue paper and a blue pen. That's just lovely. Right off the bat, you should notice that these guys are both in terms of x, which means that we're probably going to use our sideways rectangle, which means we're going to do right minus the left when we do our integration. All right, so if I just sketch a quick graph, and I'm sorry it's blue, it means that my computer is pissed off. I don't think the lighting is making it happen. If I graph this guy and solve, this is a sideways parabola, right? And so he's going to look, because it's a negative y, means it's reflected across the y-axis. It's going to look kind of like this. Boy, isn't that a pretty graph, okay? And then x equals y plus 1, you could rearrange it, and it's going to look something like this, okay? And so the area between the two curves is going to be this. And so I'm going to label this as equation 1, and I'm going to label that as equation 2, okay? And because this is a sideways, sorry, bad grammar, because these are sideways equations or equations that are in terms of x, I'm going to do, and I changed to a black so hopefully you can see it, my little rectangle is now going to be a delta y, okay? So if I set these two equations equal, again, because I can, and I'm going to do it by hand, so I set 3 minus y squared equal to y plus 1, so I get a negative y squared minus y, plus 3 minus 1 is 0. This is going to be 2, and I'm going to take out the negative, so y squared plus y minus 2 is 0, so y plus 2 and y minus 1. And so I'm going to get y is equal to 1 and a negative 2. But notice that this is in terms of, oops, you can't see it, sorry, my bad. This is in terms of y and not x. So the y value up here is going to be a 1, and the y value, I'm going to put a y right there just so we remember that it's not an x. And this is a negative 2, and again, I'm going to put a y underneath it just so you remember that it's y and not x. So now, when I set up my integral, because my rectangle is going sideways or horizontal, if we wanted to use a little bit more technical language, I'm going to integrate using my y values, and I'm going to go right minus the left. Okay, so my integral is going to be bottom to top, okay, and I'm going to write right minus the left dy, and I'm doing right minus the left because I am using a dy, and I have a horizontal rectangle. So this is going to be the integral from a negative 2 to 1 of 3 minus y squared minus y plus 1, making sure that you're careful to distribute that negative. And again, I'll just do the little negative, and then I'm going to assume you're brilliant. So this is 3 minus y squared minus y minus 1, all of that in parentheses. Clean it up just a wee bit, negative 2 to 1, negative y squared minus y plus 2 dy. And then miracles would happen because you're brilliant and you know how to integrate so very well. So my area between the curves from a negative 2 to 1 would be 9/2. And again, I don't have any units to include, so I don't have any units to report in my solution. Alrighty, that's it for today. Nice, polite start to our revolved solids. See you soon.